Unlike the Moon, Mars has several obvious volcanoes on its surface, including some of the largest ones in the solar system. While there are some individual volcanic features in several locations on Mars, the biggest concentrations of volcanic activity are in the regions called Elysium and Tarsus. Both of these are on the boundary between the heavily cratered south and the uncratered north. The Elysium volcano and several smaller ones around it are in the eastern hemisphere. Elysium is one of the older volcanoes on Mars. It probably hasn't erupted for several billion years. However, its near neighbor has lava flows that are just a few 100 million years old. This is considered quite young for volcanic activity on Mars. The Elysium volcanoes have had an impact over a continent-sized region. This image is from the Viking II landing site in Utopia, Planitia. Even though this is 1,000 kilometers from the Elysium volcanoes, many of the rocks in view are believed to be from this complex, carried here by a combination of explosive eruptions and later erosion.
The other large volcanic region is the Tarsus Bulge in the western hemisphere of Mars. This is a huge plateau, over 5,000 kilometers across, standing higher than any other part of the planet. This was probably produced by a large, hot plume of material from within the mantle, pushing the whole region upward. It's so large that it may have caused the planet's spin axis to shift, to move it closer to the equator. On top of it are several shield volcanoes, including 4 that are much larger than any volcano on Earth. 3 of these form a straight line running from northeast to southwest. At the moment, scientists are not sure why these are lined up like this. These 3 are each between 350 and 500 kilometers across and stand up to 15 kilometers above the surface of the plateau. The 4th is the largest known volcano in the solar system, Olympus Mons. Olympus is over 20 kilometers high and is 600 kilometers across. This gives it a surface area similar to the state of Nevada. The surprising thing about a large shield volcano like Olympus is that if you were standing on it, you might not notice that it was a mountain at all. The average slope is just 5 degrees, and the volcano is so large that the curvature of the planet would take the summit below the horizon if you were standing near the edge.
We can estimate the age of Olympus Mons from the number of impact craters on it. While there are no large craters on the surface here, several small ones can be found. Using this approach, astronomers have estimated the ages of different parts of the large caldera at the top. There are distinct lava flows within the caldera, and these range in age from 100 to 200 million years, substantially younger than the youngest flows in the Elysium region. However, there are other lava flows on the sides of Olympus. In this set, on the western edge of the volcano, scientists have used the same sort of crater counting techniques on individual features. Here we find flows that range from 100 million years old to just 2 million years old. From a geologic standpoint, 2 million years ago is today. This suggests that Olympus still has the potential to erupt again, even if it's just in the form of small lava flows around the base of the volcano. This is a clear indication that Mars is not quite geologically dead today, even if it's far less active than the Earth or Venus. To use a phrase from The Princess Bride, Mars is mostly dead, but not completely dead.
There are several tectonic features on Mars, but the largest one is the Mariner Valley. This is a huge extensional crack, extending more than half the diameter of the planet, in the region just southeast of the Tarsus Plateau. By any measure, Mariner Valley is enormous. If it was in the United States, it would stretch from the west coast to the east coast. It's up to 200 kilometers wide and 7 kilometers deep. If you were standing on one edge, it would be hard to see the opposite side. The Grand Canyon of the Colorado would look like a small side channel compared to this. The stretching that produced the Mariner Valley is probably related to the formation of the Tarsus Plateau. As internal heat pushed Tarsus upwards, the stretching pulled the crust apart. However, that's not the whole story here. As we look along the sides of the valley, we see lots of signs of landslides and other flow features. Mariner Valley has been widened by erosion, and there are clear signs that huge amounts of water flowed out of the eastern end at one time.
At the moment, water can't flow on the surface of Mars. The air pressure is too low, so water either freezes or boils away. But this hasn't always been true. All over the planet, we find evidence that Mars once had running water, either right at the surface or in some cases just below ground. Here are a couple of long water channels on Mars, Ma'adim Vallis and Nadadi Vallis. Ma'adim is larger than the Grand Canyon. It runs over 700 kilometers long, and it's 20 kilometers wide and 2 kilometers deep. Water in this river flowed into Gusev crater at the top of the picture, where it may have formed a lake. The Spirit rover was sent into Gusev to study the sediments produced. Nadadi is smaller, but still impressive, at over 500 kilometers long. The sinuous bends in both of these valleys suggest that they took time to form, rather than just emerging in a sudden release of water. At one time, there were rivers flowing on Mars.
Even more obvious evidence of river flows comes from this ancient river delta in Eberswald crater. Here we see where a river flowed out into an ancient lake. As the river deposited sediment, it produced a broad delta with a series of channels running through it. Today we see the delta in inverted relief, meaning that the channels are raised up and the islands in the channels are lower. That's because rock under the channels became harder than the surrounding sediment. So later erosion by wind wore away the softer rock and left the harder channels behind. Deltas only form when water flows into a standing body of water, so this is the best evidence we have of lakes on the surface. In this case, there is evidence that some of the sediment is in the form of clay, giving more clues about the nature of the river that flowed into here.
Later in Mars's history, we don't see evidence of steady rivers, but we do see signs of sudden floods of water. This huge channel is called Aras Vallis. It runs 1,700 kilometers into the northern plains and is over 100 kilometers wide. Channels like this appear to have formed in a single sudden flood rather than a long continuous flow. This suggests that something catastrophic released a huge amount of water all at once. When we look at where these channels originate, they generally start in regions of broken terrain, like the area of Margarita Vertera, shown at the bottom of this image. It appears that the ground here had a large amount of ice in it, and something caused this ice to melt suddenly, releasing it in a giant flood. The melting could have been caused by a large impact or volcanic heating from underground.
The story that Burns Cliff tells is an important one. While it seems that the general trend on Mars has been drying out, that's not the order here. Instead, dry sediment was deposited by wind first. Afterwards, water flowed over the surface and deposited the higher layers. So at this location, there was a wet period after the dry. We are coming to understand that the climate on Mars has fluctuated a lot. It's gone from wet to dry and back again many times. While the long-term trend has been towards drier conditions, it has gone the other way several times.
When we look at Mars today, it looks drier than any desert on Earth. And we know that water can't stay a liquid on the surface because the air pressure is too low. However, when we look into the soil on Mars, we find that water or water ice is still present over a large part of the planet. On this map, we're looking at the water ice in the top meter of soil of the planet's surface. It was measured from orbit by studying the way high-energy radiation interacts with the surface. As you can see, there's at least some water ice in the ground over most of the planet's surface. Near the poles, there's a lot more water ice, and this has been measured directly by the Phoenix lander. This image shows some of the ice just under the spacecraft.
Nowadays, most of the erosion that happens on Mars is due to wind-blown fine dust. This dust is mainly made of red-colored iron oxide. Since it's spread all over the planet, it's mainly what makes Mars look so red. The main way dust travels on Mars is through wind. Even though the Martian atmosphere is much thinner than the Earth, the dust grains are so small that the air can still pick them up and distribute them around the planet. Dust storms can cover a small region of the planet, or they can blanket the planet from pole to pole. Here's a dust storm seen from below. This is a set of images taken by the Opportunity rover on Mars. All of the pictures were taken around local noontime over the course of a couple of weeks. You can see how much darker the sky gets as the thick dust covers it. This dust causes problems for probes we send to the Martian surface. The dust is fine enough to get into moving parts, and if the lander uses solar panels, the dust can cover them and reduce their efficiency.
Dust storms are one example of ongoing change that has been seen on the surface of Mars. Avalanches are another one. Here we're looking at a dune field, a place where wind has pushed sand and dust into large dunes. There's red dust on top of darker sand. However, in some places the sand has broken through the dust layer and flowed downhill, producing dark streaks on the sides of the dunes. We can tell this is what's happening because the spacecraft that took the picture actually spotted a small avalanche in progress. You can see the cloud of dust it's kicking up as it hits the bottom of the slope. Here's another avalanche of dust caught in the act on the edge of an impact crater. Another feature we see on Mars is dust devils. Dust devils form when a pocket of warm, rising air begins to spin, pulling dust from the ground up with it. We see dust devils in dry locations on Earth, and they're also common on Mars, where they can be hundreds of meters across and thousands high, though most are much smaller than this. These dark streaks are produced when dust devils pull the red dust off the ground, leaving the darker rock visible underneath. Mars rovers have also seen dust devils pass, and in a couple of cases they've passed over the rovers, sweeping the dust off of their solar panels in the process. Click on the link to see a movie of a dust devil passing a rover. There may even be seasonal water gullies on Mars. On some craters, we see these narrow channels cut into the edge. They appear to have formed when water seeped out of the ground near the crater and flowed downhill a short distance. These are small enough that they would be erased if they hadn't formed recently. So erosion in several forms is still occurring today on Mars.
So what we've learned about Mars is that it used to be a warmer, wetter, and more geologically active world than it is today. The small size of Mars means that the interior mostly cooled off several billion years ago. But there is still enough heat inside the planet to continue producing small amounts of volcanic activity today, especially around the large volcanoes on the Tarsus Plateau. We also know that water used to flow on the surface. Some of this was in the form of long-lived rivers and lakes, while other flows were sudden large floods that washed over large areas before disappearing. However, there is still some water ice in the Martian crust, especially close to the poles. Currently, most of the geologic activity we see on Mars is in the form of dust and sand, being moved around by winds and flowing downhill in avalanches. Finally, while Mars has been getting drier and cooler, the change hasn't always been in the same direction. The Martian climate has varied a lot over the planet's history. One of the things that makes Mars exciting to study is that the evidence of these changes has been preserved on its surface.
Your teacher will send you a detailed map of a section of the Martian surface. In addition, you'll get a context map that lets you see where your region is in comparison with the rest of the planet. You should see if you can find evidence of at least 3 of the 4 major geologic processes on Mars and indicate where these are. Also, put together an order of events describing what happened in what order in this location. You should explain how you can tell from the information in the picture, not just base it on what you expect should happen first, second, etc. In other words, look at what features are covering or interfering with what other features. Now let's see if you understand what causes these surface features to develop. In this question, we'd like you to imagine what would happen if Mercury and Mars simply switched places. How would the geologic processes on their surfaces change as a result of this switch? Remember, we're assuming that we're taking the planets as they are now and simply moving them to different locations in the solar system. We're not changing their histories in any way. Since this one is very much about process, it's important that you explain clearly why you think things will or won't change. Just listing what would be different isn't enough here.